Economic Geology and Mineral Resources of India. Topic of the lesson: Ore deposits related to Mafic and Ultramafic rocks. Part 2: Kimberlites and Lamproites, Anorthosites, Carbonatites, and associated mineralization. Objectives: to understand mode of occurrence and mineralogy of Kimberlites and Lamproites, and formation of diamond with important examples. Mode of occurrence, mineralogy, and economic significance of Carbonatites with important examples. Mode of occurrence, distribution, and economic mineralization in Carbonatites with important examples. Kimberlites and Lamproites. Introduction. About 20% of the world production of diamonds is derived from Kimberlites and Lamproites, and the rest is extracted from beach and alluvial places deposits containing diamonds. The later released from weathering of the igneous source rocks, Kimberlites and Lamproites. Not all Kimberlites and Lamproites contain diamonds, and when present, they are present only in minute concentrations. For example, in the Kimberley mine, South Africa, 24 million tons of Kimberlite yielded only 3 tons of diamond, which amounts to an ore grade of 0.125 ppm. The proportion of gem quality and industrial grade diamonds extracted from Kimberlite and Lamproites vary from one mine to another. In 1989, the total world production of natural diamonds from both bedrock sources and placer deposits was about 97 MCT, of which about half are of industrial grade. Evans, 1993. Leading countries involved in diamond extraction are Australia, Zaire, Botswana, Russia, South Africa, Angola, Namibia, Sierra Leone, and Lesotho, and a few countries in South America. Figure 1 provides locations of the major occurrences of Kimberlite and Lamproite fields, bulk of which are confined to cratonic regions of the world. Figure 1 shows the distribution of diamondiferous and non-diamondiferous Kimberlites and Lamproites after Ferguson, 1980, Gross et al., 1987. Mode of occurrence. Most of the near-surface diamond-bearing Kimberlites and Lamproites are small pipe-like bodies, generally less than 1 square kilometer in plane view. In sectional view, they appear in the shape of inverted teardrop or carrot and become narrower and irregular at depth, some ultimately assuming a dike-like form. Most Kimberlite occurrences involve multiple intrusive events which form a cluster of a few discrete intrusions, as shown in Figure 2. Figure 2 shows schematic diagram of a Kimberlite diatreme pipe and maar volcanic crater below ground level and surrounded by a low tuff rim. The maar can be up to 2 kilometers across. After Nixon, 1980. According to Clement et al., 1984, a typical uneroded Kimberlite contains the following 3 texturally distinctive facies from bottom upwards: hypabyssal, diatreme, and crater facies. Hypabyssal facies Kimberlites are porphyritic and result from crystallization of Kimberlite magma. Diatreme facies, which may exceed 2 kilometers in depth, exhibit an explosive surface expression and contain mantle and crustal-derived rock fragments, Kimberlite lapilli, and Kimberlite fragments. In the upper levels, the diatreme facies is usually in the form of so-called agglomerate, tophacetic breccia with rounded and embayed fragments in a fine-grained matrix. The rounded fragments constitute xenoliths of garnet peridotite or eclogite from upper mantle and metamorphic rocks from deeper crust. The rounded nature of the fragments is attributed to a gas fluidized origin, Dawson, 1971. Diatreme often terminate at the surface in maars which may contain diamond-bearing maar ring-based search accumulations. Crater facies Kimberlites contain pyroclastic fallback breccias or epiclastic waterline material. The lacustrine sediments of the craters are sometimes affected by subsidence, perhaps of a cauldron nature. Some of these minerals are used as indicator minerals in stream sediment and soil samples in the search for Kimberlites. Example: red-brown pyrope, purple-red chromium pyrope, magnesium-rich ilmenite, chromium-rich diopside. Nixon, 1980. Lamproites are potash and magnesia-rich lamprophoric rocks of volcanic or hyperbyzal origin with mineral assemblages containing a few of the following primary phenocrystal and or groundmass phases: leucite, titanium-rich phlogopite, clinopyrrozine, amphibole, titanium-rich potassic richterite, olivine, and sanadine. Accessories may include predarite, apatite, nephelin, spinel, perovskite, vedite, and ilmenite. Rock 1991. Glass may be an important constituent of rapidly chill lamproites. Xenoliths and xenocrysts including olivine, pyroxene, garnet, and spinel of upper mantle origin may be present. Diamond occurs as an accessory. Fertile lamproites appear to be the silica-saturated aurindites and madupites which carry sanidine rather than leucite. Gold 1984. Diamondiferous lamproites and other lampropyrus with diamonds have now been discovered in Western Australia, Quebec, Canada, India, Ivory Coast, South Africa, Sweden, Russia, and Zambia. Mode of formation of diamonds. Kimberlites and lamproites are generally regarded as having been intruded upwards through a series of deep-seated tension fractures, often in areas of regional doming and rifting in which the magmas started to consolidate as dikes. Subsequently, highly gas-charged magma broke through explosively to the surface at points of weakness, such as cross-cutting fractures, to form the explosion vent, which was filled with fluidized fragmented kimberlite or lamproite and xenoliths of country rock. This was followed by quiet emplacement of magma as shown in figure 2. Extremely high temperature 1400 to 1600 degrees centigrade and pressure 50 to 70 kilobar are required to form diamond from pure carbon in areas of 60 km thick continental crust. The approximate depth range for diamond genesis is 100 to 300 km. Evans 1993. For many decades, there has been a very active debate as to whether diamonds crystallized from the magmas, which cooled to form igneous rocks, kimberlites or lamproites, in which diamonds are now found as phenocrysts, or whether they were picked up by these magmas as exotic fragments, xenocrysts, from diamond stability fields in the upper mantle, that is, passenger-locomotive relationship. According to Gurney 1990, the most prospective areas for diamond exploration are on cratons, stabilized by 3.2 billion years. Diamond-bearing zones in kimberlites dwindle away from such core zones. Radiometric ages of the inclusions in diamonds suggest that, in many cases, the xenocrysts of diamonds are much older than the magmas that transported them to the surface. Richardson et al. 1984. Dating of garnet inclusions in diamonds in two approximately equal to 90 million year old kimberlites of South Africa indicated that diamonds are older than 3000 million years, suggesting that diamond hosts in upper mantle are also older. Geologic ages of kimberlite and lamproites range from middle Precambrian through Mesozoic. Available data on the inclusions in diamonds clearly indicate two main periods of diamond formation. The first about 3300 million years ago and the second about 1580 to 990 million years ago. The dated inclusions in the first group of diamonds were peridotic minerals and in the second group were eclogitic minerals. These data indicate that diamonds grew stably within the upper mantle in eclogite and ultramafic rocks. The growth of diamonds occurred in a layer between 132 and 208 km depth beneath continents and 121 to 197 km beneath oceans, provided that carbon was present. Thus, any magma that samples a diamondiferous zone of the upper mantle may bring diamonds to the surface if it moves swiftly. The speed of ascent of such magmas has been calculated to be around 70 km per hour. Mayer 1985. Slow ascent could follow time for the resorption of diamonds by transporting magmas as the pressure decreases. Delta carbon-13 values of eclogitic diamonds indicate recycling of crustal carbon back into the mantle by subduction. Gurney 1990 suggested that the subducted material was underplated during the Proterozoic as eclogite onto the existing diamondiferous Archean peridotic keels of cratonic areas in which peridotic diamonds had formed 3.2 billion years ago. Diamondiferous layers in the upper mantle in lithosphere at the boundary between lithosphere and asthenosphere are probably discontinuous, and absence of the layers may account for the absence of diamonds in many kimberlites. Kimberlite magmas generated at shallow levels also do not carry diamonds. Example, kimberlites in New South Wales, Australia generated at 60 to 70 km depth. Some examples. In Western Australia, diamondiferous kimberlites and lamproites numbering over 100 are encountered in 3 distinct provinces of Kimberley Craton. In Lesotho, 2 kimberlitic pipes in a cluster of non-productive kimberlites are the main source of large and gem-quality diamonds. In Siberia, Russia, kimberlites exhibit a regional zoning. A central zone of diamondiferous kimberlites is surrounded by a zone of pyrope and low diamond values, followed by a zone barren of diamonds with pyrope, and finally an outer zone in which neither of these high-pressure minerals is present in the kimberlites. These kimberlites range in age from Precambrian through Mesozoic. Of them, the Paleozoic kimberlites are most productive, as shown in Figure 3. Figure 3 shows distribution of kimberlites in East Siberian Craton showing different mineralogical facies. The places marked as A show diamond, B show diamond pyrope, C shows pyrope, and D shows other kimberlites. Modified after Dawson 1980. Carbonatites. Carbonatite complexes consist of intrusive magmatic carbonates and associated alkaline igneous rocks. They range in age mainly from Proterozoic to recent and belong to alkaline igneous provinces. Mode of occurrence. Carbonatites are generally found in stable cratonic regions, sometimes with major rift faulting, example East African Rift Valley and St. Lawrence River Graben. There are, however, exceptions where carbonatite complexes are not associated directly with any alkalic rocks, example Sangu complex, Tanzania, and Kau, Zambia. Further, not all alkalic rock provinces and complexes have associated carbonatites. Among the known carbonatites, about 330, less than half occur in rift valleys, and remainder being spatially related to major faults traversing cratonic regions and some in fault intersections. Example, Northern Karelia Alkaline Province, Russia. Carbonatites often form clusters or provinces within which there may have been several episodes of activity. Example, the East African rift valleys where late Proterozoic, early Paleozoic, and Cretaceous carbonatites occur. Ore-bearing carbonatites are encountered as volcanic and plutonic bodies in dilatant fractures at places replacing earlier carbonatites and silicate rocks. Carbonatites are normally emplaced later than the bulk of alkalic silicate rocks with which they are genetically related. Many carbonatite occurrences are cylindrical, pipe-like, and prominently concentrically zoned, such as Palabora Igneous Complex, South Africa. A few are regularly shaped unzoned bodies like that at Mountain Pass, California. Some carbonatite complexes appear to be highly differentiated rocks occurring near and with sinites and other alcoholic lithologies, but others appear to be undifferentiated, occurring with curious diopside, olivine, pyroxenite, Harsbergite intrusives. Some carbonatites are associated with barren kimberlites, generally within rifted cratonic interiors, suggesting deep crustal or upper mantle processes involving carbonatitic liquid separation and injection or some other form of mantle degassing. Economic aspects. Carbonatites are exploited for phosphorus from apatite, magnetite, niobium, pyrochlore, zirconia, and rare earth elements, monzonite, bastnasite. To date, only one carbonatite complex is a major producer of copper, Palabora, South Africa. Other economic minerals in carbonatites include fluorite, barite, and strontianite. Carbonatites supply most of the world's niobium, Brazil, Canada, REE, USA, China, and vermiculite, South Africa. Till 1993, about 22 mines were in operation in 19 different carbonatites in 14 countries. The African carbonatite complexes at Sukulu, Uganda, Dorowa, Zimbabwe, Chilwa Island, Malawi, Glenower, South Africa, Murma Hill, Kenya, and Ukursu, Namibia contain large resources whose potentials await further appreciation. In India, the niobium-rich pyrochlores in the Savatur and Jogipati districts of Tamil Nadu constitute potential resources. Some occurrences. Palabora Igneous Complex, South Africa. The Palabora Igneous Complex, carbon 2047 million years, lies in the Archean terrain of the Transvaal. It resulted from alkaline intrusive activity involving initial emplacement of a large body 6 km by 2.5 km of apatite-rich phlogopite pyroxenite. It is kidney-shaped in outcrop but forming a pipe at depth and is surrounded by a narrow, approximately equal to 30 meter wide envelope of a feldspathic pyroxenite and an outer discontinuous, approximately equal to 40 meter wide zone of phenite, potassium-rich orthoclastites, a hydrothermal alteration assemblage, as shown in figure 4. The figure 4 shows geological map of Palabora alkaline complex, South Africa. The areas marked 1 show an open pit operation of Forsker which produces phosphate. 2 shows vermiculite open pit and 3 shows the Palabora open pit at Lulkscoop which produces copper, magnetite, etc. The northern part of the apatite-rich pyroxenite body is intruded by apatite-poor phlogopite pyroxenite, phlogopite pyroxene pegametoid and serpentine phlogopite pegametoid, as shown in number 2 of figure 4. The central and southern parts of the apatite-rich pyroxenite are invaded by phlogopite pyroxenite apatite pegametoid. The later, in the central part of the main apatite-rich phlogopite pyroxenite body, is further invaded by phoskerite, magnetite, olivine apatite rock and banded carbonatite, resulting in the formation of Lulkop carbonatite phosphorite pipe, as shown in figure 4 number 3. Fracturing of this pipe led to the intrusion of a dike-like body of transgressive carbonatite, as shown in figure 5, and development of a stockwork of sulfide-rich carbonatite veinlets. The figure 5 shows geology of the 122 meter level Lulkop carbonatite complex, Palabora, South Africa, modified after Jacobson 1975. These near-vertical veinlets occur in parallel trending zone up to 10 meter wide, although individually the veinlets are usually less than 1 centimeter wide and do not continue for more than 1 meter. The sulfide-rich veinlet zone extends vertically and continuous beyond 1 kilometer below the surface. The chalcopyrite and carbonite-bearing carbonatite veinlets, according to Aldues 1986 and Erickson 1989, were crystallized possibly from sulfide-rich fluids separated from pyroxenite through the process of liquid immiscibility, liquidation. Evidences include presence of copper sulfides, interstitial between large carbonate grains, and sulfurization of older magnetite into pyrohitite plus or minus pyrite by late stage action of copper plus gold plus silver plus REE and sulfur bearing fluids. There are 3 separate large mining pits at Palabora, pit numbers 1, 2 and 3 as shown in figure 4. Pit number 1, Fosker's pit, which covers only part of the apatite-rich pyroxenite, contains large reserves of apatite. In 1984, Fosker's pit produced 2.6 million tons of phosphate apatite concentrate, nearly 9,000 tons of badylite concentrate and 43,000 tons of copper concentrate. The neighboring pit number 2 constitutes the second largest vermiculite mine in the world. In 1990, it produced nearly 218,000 tons of concentrate. The ores from pit numbers 1 and 2 are also providing the following minerals as co-products: magnetite, uranium in uranothorite, cobalt in lignite, and zirconium hafnium in badylite, and trace amounts of nickel, gold, silver, and PGM. In the Lulco pipe, as shown in pit number 3, the carbonatite and phosphorite are worked for copper with byproducts of magnetite, apatite, gold, silver, PGM, badylite, uranium, nickel, sulfate, and sulfuric acid. Mountain pass occurrences, California. The mountain pass carbonatite 1400 million years occurs within the Precambrian Rocky Mountain area. The deposits lie in a belt about 10 km long and 2.5 km wide. The metamorphic country rocks have been intruded by potash-rich igneous rocks, granites, sinites, and shawkinites. The REE-bearing carbonatites of the mountain pass region are related spatially and probably genetically to these potash-rich igneous rocks. Olson et al. 1954. In the mountain pass region, a shawkonite sinite body known as the sulfide queen carbonate body, 730 meter long and 200 meter wide, carries a large concentration of rare earth elements as shown in figure 6. The figure 6 shows simplified map of the mountain pass region, the sulfide queen carbonate body, Mountain Pass District, California, after Olson and Prey 1954. The rare earth elements are carried by bastonsite and parasite. These minerals being in veins that are most abundant in and near the shawkonite sinite body. Most of the 200 veins that have been mapped are less than 2 meter thick. Carbonate minerals make up about 60% of the veins and carbonatite bodies. They are chiefly calcite, dolomite, anchorite, and siderite. The other constituents are barite, bastnasite, parisite, quartz, and variable small quantities of 23 other minerals. The REE content of much of the ore body is 5 to 15%. The sulfide queen carbonate body is the largest ore body of rare earth minerals in the world at present under exploitation. Kola Peninsula, Northern Karelia Alkaline Province, Russia. Alkaline igneous complexes and their associated carbonatites show a broad spatial relationship to areas of hotspot activity which may be accompanied by dooming and fracturing, the Kola Peninsula being an excellent example. The upper Paleozoic alkaline igneous and carbonatite complexes of this region host a number of extremely large ore bodies, of which the most important are Kibina, Koudur, and Sokli. Kibina is a ring complex about 40 km across with inward dipping, layered intrusion of various alkaline rock types. One apatite nepheline ore body forms an accurate irregular lens-shaped mass with a strike length of 11 km and a proved dip extension of 2 km. The thickness ranges from 10 to 200 meters, average of 100 meter, and at least 2.7 billion tons of ore, averaging 18% phosphorus pentoxide are present. The apatite concentrates contain significant strontium oxide and rhenium oxide values. Nepheline concentrates are also produced for the manufacture of alumina. Russia is the world's second largest producer of phosphate rock, with much of its production coming from Kibina. The Koudur carbonatite complex, as shown in figure 7, consists of different alkaline and basic rocks, turgite and melilitite, ijotite, meltigite, and pyroxene olivine rock, and pyroxenite and nepheline pyroxenite. Apatite, forsterite rocks, and magnetite ore body were emplaced at a later stage. Ores on an average contain 36% iron and 6.6% phosphorus pentoxide. Badylite forms a byproduct. Figure 7 shows sketch map of part of the western section of the Koudur complex showing position of the magnetite ore body after Rimskaya-Korsakova 1964. Vermiculite is also produced. In its mineralization and rock types, this complex has affinities with Palabora carbonatite complex described earlier. Sokli complex is located in Finland across the border of the Kola Peninsula. With an areal extent of about 18 square kilometer, It is one of the world's largest carbonatites and it is remarkable for its partial cover of residual ferruginous phosphate rock forming an apatite francolite regolith of a type Itharto regarded as being of tropical origin. Provided reserves are over 50 million tons averaging 19% phosphorus pentoxide. The residual cover vary from a few meters to 70 meters in thickness. Pyrochlore with both uranium, tantalum and thorium enrichments occur in the carbonatites with apatite magnetite mineralization is encountered in metaphosphorites. Kimberlitic dikes are also present but no diamonds have been found. The carbonatite intrusion tapers downwards from a diameter of 6 km at the surface to about 1 km at a depth of 5 km. This feature also suggests that at great depths, carbonatites, like kimberlites, become dike-like bodies within the deep fracture zones that have tapped the levels in the mantle from which these alkaline rocks and their rare earth and associated elements have probably been derived. Samoilov and Pliusin 1982. Anorthosites. Anorthosite is practically a monomineralic rock composed of 90% or more of intermediate to calcic plagioclase. Mineralogy and mode of formation. Two kinds of the nearly monomineralic plagioclase rocks of AN35 or more are encountered. The layered rocks near the upper portions of some layered igneous complexes, for example Bushveld complex, which formed after the mafic minerals had crystallized and sunk, or by the floating of plagioclase crystals within the magma chamber, and the so-called anorthosite massifs, plutons, typically containing plagioclase that is andesine or labradorite. The anorthosites of layered igneous complexes developed by gravity stratification in ultramafic to mafic complexes are characterized by rhythmic layering, show many cumulative textures, are free of megacrysts and are composed mostly plagioclase in AN 70 to 100 range. Anorthosite massifs are of economic significance as they are the major sources of titanium-bearing minerals, namely ilmenite, about 52% of titanium oxide, and rutile, more than 95% titanium oxide, along with the fluvial and marine placer deposits derived from them. Widespread accessory ilmenite and commercial concentrations of ilmenite in the anorthosite massifs indicate a genetic relationship between ilmenite and anorthosite. Dikes and veinlites of ilmenite in anorthosite as well as inclusions of anorthosite in the ore bodies attest to the younger age of the ore. Dearden 1958 suggested that the ilmenite and the anorthosite are differentiates of the same parent magma. The larger deposits of commercial grade ilmenite ore representing a late state segregation. Occurrence and distribution. Available data indicate that anorthosite massifs are geochronologically and tectonically constrained. These mafic calcium-rich rocks are all Proterozoic in age at 1.3 plus or minus 0.2 billion years and are confined to terrains of anorganic intracontinental rifting or incipient rifting tectonic setting in a broad belt across North America, Britain and Scandinavia. Figure 8 shows the locations of the major occurrences of predominantly ilmenite-bearing and a few rutile-bearing anorthosite massifs of the northern hemisphere. Anorthosite massifs are divisible into two groups, according to Hers 1976, based on their plagioclase and oxide compositions. They are labradorite anorthosite massifs characterized by plagioclase of anorthite 6845 composition and either titanomagnetite or its oxidized equivalent magnetite ilmenite, for example, Michigamme anorthosite, Labrador, Duluth-Gabbro complex, Minnesota, and andesine anorthosite massifs containing plagioclase anorthite hemo-ilmenite and enstatite anorthite, that is, enstatite content of pyroxene, anorthite content of plagioclase, greater than 1. The latter is associated with the world's principal ilmenite deposits. For example, anorthosite massifs of Adirondack Mountains in New York, Allard Lake region in Quebec, Canada, and Rossland in Virginia, USA. Titanium-rich minerals crystallize late in the magmatic history of Anorthosite complex. The behavior of titanium during crystallization of magma is controlled by several factors, including the initial abundance of titanium, the changing chemical activities of silicon, aluminum, and iron, the variable partial pressures of oxygen, the possible formation of titanium-rich immiscible liquids, and temperatures of crystallization, according to Verhoeven 1962. Studies carried out on the magnetite ilmenite deposits near Lake Sanford, Newark, indicate that these ores are differentiates of an anorthosite gabbro magma. The ores are thought to have formed from segregations of a magnetite ilmenite liquid, part of which was trapped and crystallized in interstices between crystals of plagioclase and augite, but much of which was tectonically squeezed through the process of filter pressing. The iron titanium oxide liquid was injected into adjacent locally still plastic gabbros and anorthosites, locally forming high-grade iron titanium oxide ores. Some examples. Lac Tio ilmenite deposit, Allard Lake District, Canada. The Lac Tio deposit contains about 125 million tons of ilmenite ore, 30-35% of titanium oxide, and was considered as the largest body of titanium ore till the discovery of another still larger deposit in Norway. In the Lac Tio deposit, ore bodies from irregular lenses, narrow dikes, large sill-like masses, and various combinations of these forms. Some of these clearly cut the anorthosite and appear to be later in age. The Lac Tio ore contains crystal aggregates of thick tabular ilmenite grains up to 10 mm across and 2 mm thick. Minor amounts, generally about 5% of plagioclase, pyroxene, biotite, pyrite, pyrrhotite, and chalcopyrite make up the interstitial material. Ilmenite grains contain exsolved hematite, and the later ranges in sizes from fine grains to blebs up to 10 mm in diameter. The ilmenite contains up to 25% of intergrown hematite, and the ilmenite-hematite mixture is so fine-grained that grinding cannot effectively separate the two minerals. Telnes ilmenite deposit, Norway. The world's largest ilmenite ore body is located at Telnes in the anorthosite belt of southern Norway, about 120 km south of Stavanger. The deposit is boat-shaped, 2.3 km long, 400 m wide, and about 350 m deep, as shown in figure 9. The ilmenite-norite ore occurs in the base of norite. The ilmenite-norite, along with the associated norite, includes the main body of anorthosite, cross-section as shown as CD in figure 9, with which it has sharp contacts. Figure 9 shows the map and sections of the Telnes titanium ore body after Dybdahl 1960. The ilmenite-norite intrusion shape is apparently an original feature of the intrusion. Ilmenite carries up to 12% hematite as egg-solution lamella, as shown in figure 10. Proven reserves are 300 million tons. The ore contains 18% titanium oxide, 2 volume percent magnetite, and 0.25 volume percent sulfide, pyrite, and copper-nickel sulfides. Figure 10 shows egg-solution bodies of hematite-rich material in an ilmenite-rich base in Telnes, Norway. Summary. About 20% of the world production of diamonds is derived from Kimberlites and Lamproites, and the rest is extracted from beach and alluvial places deposits containing diamonds. Kimberlites and Lamproites are carrot-shaped and are generally regarded as having been intruded upwards into cratonic areas through a series of deep-seated tension fractures, often in terrains of regional doming and rifting. Two main periods of diamond formation. The first about 3,300 million years ago and the second about 1,580 to 990 million years ago. Inclusions found in diamonds indicate two periods of diamond formation. The first about 3,300 million years ago and the second about 1,580 to 990 million years ago. Peridotite and eclogitic minerals found as inclusions indicate that diamonds grew stably in eclogites and ultramafic rocks confined to discontinuous diamondiferous zone, diamond stability field of the upper mantle. Geological ages of 13 Kimberlites and Lamproites are much younger than the diamonds they contain, and this feature indicates their role as a carrier of diamonds from 100 to 300 km deep upper mantle to near surface environment. Carbonatites are generally found in stable cratonic regions along major faults and fault intersections, and rift valleys. Anorthosite massifs are essentially Proterozoic in age and confined to terrains of anorogenic intercontinental rifting or incipient rifting tectonic setting in a broad belt across North America, Britain, and Scandinavia. Anorthosite massifs are divisible into two groups according to Hers 1976, based on their plagioclase and oxide compositions. They are Labradorite anorthosite massifs, for example, Michigamme anorthosite, Labrador, Duluth Gabbro complex, Minnesota, and andesine anorthosite massifs, for example, anorthosite massifs of Adirondack Mountains in New York, Allard Lake region in Quebec, Canada, and Rossland in Virginia, USA. Anorthosite massifs are the major source of titanium minerals, ilmenite and rutile.